Assalamualaikum warahmatullahi wabarakatuh. Okay, today we will discuss a new chapter, that is chapter 3, Dynamics. Firstly, the lesson outcome. Number 1, students should be able to define force. Number 2, students should be able to state and apply all the Newton laws of motions in problem solving. Number 3, students is able to define linear momentum. And number 4, students should be able to state and apply principle of conservation of linear momentum in problem solving. Definition of force. A force is defined as a push or pull that one object exerts on another. When more than one force acts on an object, the resultant motion of the object is determined by the magnitude and direction of the net force acting on the object. The net force is therefore defined as the summation of all forces that acted on the object. Type of forces. There are two main types of forces, the long-range force and the constant force. For the long-range force, do not require the two objects to be touching, can exist even if the two objects are far apart or even if there are other objects between the two. Example, gravitational force, magnetic force, and electric force. The second type of force is the contact force, which exists only if the objects are touching one another. And the example are the reaction force, the tensional force, and the frictional force. And now we go into detail the four common types of forces existing when an object is in motion. Okay, number 1, the gravitational force. Okay, the main equation is W equal to mg, where W is the weight of the object, g is the gravitational acceleration of the object. W and g always points downward towards the Earth core. The magnitude of g is 9.81 meter per second squared. The second force is the reaction force. It's a force produced when the surface reacts to a force applied on it. Its direction is always out of the surface. If the applied force is perpendicular to the surface will produce a reaction force that is perpendicular and out of the surface. The third force is the tensional force. It's the force transmitted through a string, rope, or wire when it is pulled tight by forces acting at both ends of the string. It's directed along the string, away from the ends, and pulls the objects on either end of the string with the same magnitude T. For a string pulley system, the cord and the pulley is taken as massless, and the cord is inelastic and it runs around a frictionless pulley. And the fourth one is the friction force. The equation F equal to mu r is a force exerted by a surface to resist the motion of an object on it. It always acts in the opposite direction to the motion of the object. Now let us discuss the three Newton's laws of motion. Newton's first law. Every object continues in a state of rest or of uniform motion in a straight line unless acted upon by external forces to change that state. Here, external forces means the net force. This means if the net force on the object is 0, the object will remain in its initial state of motion, that is, either at rest or motion with constant velocity. With this in mind, Newton's first law is also known as the law of inertia. and for any object, its mass is its measure of inertia. Let us discuss example 1. Okay, a horizontal force of magnitude 70 Newton is applied to a box of mass 20 kg resting on a rough surface. Does the box slide? Okay. Here is the free body diagram of the whole system. We can see that there are 4 forces acting on the box simultaneously. The reaction force R, the pulling force F, the friction force FF, and the weight of the object W. From the free body diagram, it is clear that the box will only slide if the applied force F is bigger than the frictional force FF. So our next step is to determine the magnitude of the friction force compared to the applied force on the box. Okay, so what we do is we apply the equilibrium of force along the vertical axis. So we get R equal to W, which is equal to mg, and we have R equal to 169 Newton. From the equation of the frictional force F equal to mu R, we get the frictional force to be 78 Newton. So it shows that the frictional force is bigger than the pushing force. So the conclusion is the box does not slide. Example 2. A warehouse worker pushes a 25 kg crate along a rough floor at a constant velocity with a force that points downward at an angle of 45 degrees below the horizontal. If the floor exerts a 5 Newton friction force on the crate, calculate the magnitude of the pushing force and the reaction force. Okay, step number 1. Since the crate moves with constant velocity, the net force, which is F net equal to ma, equals 0 Newton. So this will result in the summation of force along the y-axis, Fy, and summation of force along the x-axis, Fx, equals 0. And we can see from the free body diagram given there, all the forces and their orientation relative to the object. The second step, from equation 2, okay, we can determine the magnitude of the pushing force applied to the crate. Okay, by rearranging the equation, we get F equal to 7.07 Newton. And the third step, from equation 1, again, we did the same thing, that is, rearrange the equation and substitute the values into the equation to get the reaction force R to equal 250.25 Newton. Now let's look at Newton's second law. The acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass. The direction of the acceleration is in the direction of the net force, and here is the vector form of the Newton's second law, which is F net equals ma, and we can see that on the left and the right side of the equations both have the same sign, indicating both sides of the vectors are always in the same direction. The definition of F net, M, and A given there. Okay, so we look at an application of Newton's second law in example 3. The figure there shows an Atwood machine consists of two masses, M1 0.55 kg and M2 0.8 kg. Both masses are suspended from a fixed frictionless pulley. Calculate the acceleration of the system. Okay. M1 will fall and M2 will rise with accelerations of the same magnitude. The direction of the acceleration is shown in the figure there. The positive direction is taken to be the direction of the motion of both masses. Applying Newton's second law for M1, okay, we have summation of Fy equal to T minus M1G equal to M1A, whereas summation of Fx equal to 0 since there is no motion along the x-axis. And we did the same thing to M2, where summation of Fy T minus M2G equal to minus M2A, and summation of Fx is also equals 0. And from equation 1, T is equal to M1A plus G. Replacing T in equation 2, we get the acceleration of the system to be 1.8 meter per second squared. Example 4. A force of 50 Newton is applied at an angle of 30 degrees to the horizontal on a 0.75 kg block at rest on a frictionless surface. What is the magnitude of the resulting acceleration of the block and the reaction force acting on the block? Okay, so the first step is draw the free body diagram of the whole system. We can see that there are three forces acting on the object, which is the reaction force, the weight of the object, and the pushing force F. The object moves along the positive x-axis. So from the Newton's second law of motion, the summation of force along the y-axis will equal 0. Whereas for the summation of force along the x-axis will equal ma. Okay. For the next one, acceleration of the block exists only along the x-axis. The sum of forces in the y direction therefore must be 0. From the free body diagram, we substitute the values that we know to get the acceleration of the system to be 17.3 meter per second square, and the reaction force can be calculated from equation of Fy to get R equal to 14.9 Newton. Now we look at Newton's third law of motion. For every force which is action, there is an equal and opposite reaction. The action force and the reaction force of Newton's third law are equal in magnitude, opposite in direction, and acts upon different bodies. And this statement can be written in the given equation here, where we can see the sign on the left and the right of the equation is different, meaning the vectors on the left and the right side of the equation acts in the opposite direction but have the same magnitude. That's all for the first part. Thank you for your attention. See you in our next video. We will discuss linear momentum.